This is a clip from our show with Professor Max Welling.
The first thing I want to say, there is no machine learning without assumptions. It just basically, you have to interpolate between the dots. And to interpolate means that you have to make assumptions on smoothness or something like that. So the machine learning doesn't exist without assumptions. I think that's very clear. But, clearly it's a dial, right? So you can have, on the one end, you can have problems with a huge amount of data. It has to be available clearly. And there you can dial down your inductive biases. You can basically say, let the data do most of the work in some sense.
Now, I think it's a good thing to build intuition about machine learning principally as an interpolation problem, right? So we're given the training data and we need to cleverly interpolate between the training examples to reason about the statistical context of the test examples. This is what machine learning is in a nutshell. And actually, a researcher friend of mine from Meta AI Research in Silicon Valley, a guy called Dr. Thomas Lukes, he published a paper a couple of years ago called Interpolation of Sparse High-Dimensional Data. And he showed that it was indeed possible to perform competitively with multi-layer perceptrons for a regression problem using pure play interpolation methods like Voronoi and Delaunay triangulation and spline methods. I mean, think of creating simplexes of the nearest neighbors around your training data and then averaging the results together. This simple method works remarkably well up to about 30 dimensions. Obviously, eventually it gets deranged by the curse of dimensionality, but as we'll discover slightly later, neural networks might have a slight advantage over pure play simplex interpolation just because they work principally by figuring out boundaries of the input space to exclude. So, if you're on the zero side of the ReLU, that is. So that helps a lot in high dimensions when you have a poor sampling density in a particular region of the input space. But anyway, if you do principally think of machine learning as being an interpolation method, it raises some interesting ideas. Thomas said to me that the crux of the problem is that we're trying to approximate a function that has spatially unique behavior in more than about 20 or so dimensions. Like in that case, it's hopeless. There's no question about it. He says that you can increase the data density, like in 100 dimensions, but to get a grid with 10 points on a side, which is to say 10 to the power of 100, there aren't enough protons in the universe that could convexly cover it. So Thomas concluded by saying what this means is that everything that we do successfully approximate now with millions or billions or even trillions of data points, which accounts for a lot of the successes in machine learning, these data sets only have spatially novel behavior in very few dimensions. Right, or a varying gradient in very few dimensions, 16 or fewer. If we suppose that the true function has a varying gradient in more than that many dimensions, there's simply not enough data in the world to approximate it. The mathematics here is unequivocal. So what actually happens when the test examples are outside the convex hull of the training data? What happens when we're in an extrapolative regime? Well, it's increasingly impossible in high dimensions for